Welcome, my friends. In this video, I will be completing a dice rolling simulation in Google Sheets to verify the central limit theorem and then creating a normal distribution probability model. So as is always the case, you can access this Google Sheets file through the link in the description. If you'd like to edit this, you can go to File, Make a Copy, and you can rename this copy whatever you'd like to name it, maybe with your last name at the end or whatever you would like. And then once you make a copy, you should be able to edit this document. So in this first sheet here, we're going to try to verify the central limit theorem, or basically do an experiment that kind of explains some of the ideas related to the central limit theorem. So the central limit theorem basically says that for any probability distribution, the sample mean is going to follow a normal distribution as long as we have a large enough sample size. I know that's just a whole bunch of words there that might not make a lot of sense just saying it, but basically what we're going to end up doing here is we're going to generate a whole bunch of sample means here from rolls of the die, and if we plot all of those means together, that should follow a normal distribution, and we will verify that with a histogram. So first of all, I'm going to do 200 different samples here. So here in this very first row, I'll zoom in a little bit here. I'm going to create the numbers 1 through 200 to represent a sample size, or not a sample size, but a number of samples of 200. So I'm going to do this by entering 1 in the very first cell. This is B1. And then in the next cell, C1, I'm going to type equals. And then I'm going to click on B1, and I'm going to do plus 1. I could also have just type 2 and then grab these two, and I'm going to end up dragging these to the right. That would be one way to make this work. But since I have to go so many cells this way, it's kind of a drag to drag it, no pun intended there, a drag to drag this all the way out there. So kind of a shortcut here is if you just actually just click on the C2, which has this formula here, B1 plus 2. I kind of want to extend that all the way until I have 200 of these. I can just scroll this to the right. And I've already kind of formatted this. We really just have to go to GS. If I hold down Shift, I'm holding down Shift right now, and I click on GS1, I will have highlighted all of those values. And now if I hold down Control and press Enter, or if you're on a Mac, it would be Command and press Enter, and that will copy that formula all the way through. Now, if that's not working for you, or you want another way to do this, you could just grab this first one and you could just drag it all the way to the right. But that's kind of a while to drag that, right? So it doesn't go all that fast. So it's kind of up to you which way you want to go up. Go ahead and do that. Let me get this back one more time. So let me drag over here, click on this while holding down Shift, and then Enter, and then I've got my 200 samples kind of set up, right? And we're going to be simulating dice rolls, and for the roll of a die, there are of course 6 different outcomes. 1, 2, 3, 4, 5, or 6 on a fair 6-sided die. And each of those is equally likely, so to calculate the mean, we can just find the average of the numbers from 1 through 6. This is the theoretical mean. Later we'll do the actual experiment. But theoretically, if we just add up the numbers from 1 to 6 and divide by 6, we will find the mean. So we could do that formula in here, but instead I'm going to do this with the average function, and I can just average the numbers from 1, 2, 3, 4, all the way through 6. And if I type that in there, that will basically just add up those 6 numbers and divide by 6, and the result does end up being 3.5. Now I could, and actually I'm just going to drag this one to the right as well. It's going to be 3.5 for every sample. So no matter what, the theoretical mean for rolling 6 dice, or I guess any number of dice in a 6-sided die, the theoretical mean is always going to be 3.5. So I'm going to drag this all the way over here. I'm going to go here, and I'm going to click on GS while holding Shift, and then press Control and Enter, and that will complete the formula there. Okay, we're not quite ready for the experimental mean yet, but we can calculate the theoretical standard deviation. So to find the standard deviation, we can just use the standard deviation dot p formula, so equals standard deviation dot p. And this is going to find the standard deviation of an entire population. The reason we can use the one for population is because the only 6 outcomes for a roll of the die are 1 through 6. That's the population, every single possible number you could roll on the die. We don't have a sample here, we have a population, meaning we should use this version with the p. So I can type in the numbers 1, 2, 3, all the way through 6, and that's going to give me the theoretical standard deviation of 1.71. I'm going to scroll over here. I'm going to hold down Shift, click on GS7, and then hold down Control and press Enter. All right, we are almost ready to actually create our samples here. So let's go under observation number, and we're going to take a sample of size 100 for each sample. So we're gonna generate 200 samples, but each of those samples is going to have a sample size of 100. So I'm gonna type 1 here, and it's a little easier to drag going down than going to the right. So I'm just gonna I'm gonna type in the 2. I'm gonna highlight 1 and 2, and I'm just gonna drag this down. So since this is a little bit faster going down than left to right, I can just drag this down. And I think I have to go through, looks like 111 here to get a sample size 100 there. So now I have the numbers from 1 through 100. And now I can generate the actual random sample here for each die roll. So here's my very first sample. And actually, maybe at this point, I'm gonna go ahead and freeze my panes maybe before I do that, because right now I notice that if I scroll down, I can't really see which sample I am on anymore. And if I scroll to the right, I can't see which observation I am on anymore. So kind of a fix for that is to freeze the first row and the first column. And the way you can do that is to go to the view and then select freeze and freeze one row. And then go to view one more time, go to freeze, and then go to one column. And now you'll see that if I scroll down, that first row is frozen there in that we can always see that first row. And also similarly, if we scroll to the right, we can see this very first column all the time. Okay, now we are ready to generate our samples here. So we're going to use the random between function to generate our samples. So if we type in equals rand between, in open parentheses, we want a random number between 1 and 6. That's going to represent our die roll. So I'm going to type in 1, 6, close my parentheses, and I'm going to have a random number between 1 and 6. It looks like I got a 3, right? And I can either drag this all the way down, or I can scroll all the way down through 100, hold down Shift, Control, and press Enter. So either way, however you want to do this. But then we also have to, that was for our first sample, so now I've generated, 100 die rolls for the first sample, but I want this to happen 200 times. So once I have this highlighted, the very first sample, I can scroll this all the way to the right until I get through my 200th sample. I can hold down Shift and click on GS 111, and then press Control and then Enter to complete that formula for all of those cells. Now I'm not going to click off this yet because right now, well actually I'm going to click it off just to show you that now I have generated all of these samples, but anytime that I type anything into any cell, these are going to be kind of like regenerating, and I don't want it to happen that way. So to kind of get around that, we can basically copy and paste the values. So right now, each of these cells the back end of the cell is showing the random between function, and the front end is showing the result of that function, right? So what we want to do is basically copy each value in these cells and paste just the value so that we no longer have the formula on the back end. So the way to do that is we need to highlight all of these cells. So if we click on B12 and then hold down Control and Shift and press the down arrow, still hold down Control and Shift and press the right arrow, we all have copied everything. You can either do Control C or right click and copy. I'm going to right click and copy there. And now I've copied all those numbers. And now if I scroll back to B12, I can right click on B12 and paste special values only, or I could do the Control Shift V. And once I press that, you will notice that now the cells no longer have the random between functions. They've just pasted the values. So now when I type things in any of these cells, they will not change. So now we have kind of like this static simulation here. All right, so now we've completed our simulation here. So we have our experiment or our sample. We have a sample of size 100, and we've done that 200 times. So we have all of these dice rolls here, and now we can go ahead and calculate our experimental mean. So our experimental mean will be different for each sample. So we can do this by taking the average, so equals average, and then we'll want to highlight all of these numbers. So hold down Control and Shift and press the down arrow. And we only want the very first sample here, so we can press Enter, and that will give us my very first experimental mean. So it turns out, the theoretical mean should have been 3.5, but this very first sample, turns out it was a slightly higher mean. It was 3.54. And I can go ahead and drag this all the way to the right for my 200, but the faster way is going to be to scroll all the way to 200, hold down Shift, click on that cell, and then hold down Control and press Enter. And now you can see I have my mean for every single one of my samples here. So this one's a little bit higher than 3.5, a little bit lower. So we knew they could deviate a little bit from that true theoretical mean, and so that's what we're seeing here in this in the second row. And now we want to know, how close were we on each one. So we can calculate the difference. So the difference is going to be equal to the experimental mean minus the theoretical mean, right? So I'm just using the arrow keys to get around here. So the first one, the experimental mean was 0.04 higher than the theoretical mean. Or the next one to the right, if I drag this one to the right, this one was actually, 0.02 below. And once again, I can scroll all the way to the right, having selected the first one there. Hold down Shift and press Control, and then press Enter. And that will have completed that for every single one of them. And then we can do a similar thing for the experimental standard deviation. So let's find the standard deviation of each of these. It should be 1.71 theoretically, but it's probably going to be off by a little bit. So we'll do equals standard deviation, and we don't need the one .p anymore because now we're doing it based on a sample. You can use the one that's .s, or I believe this one right here, the standard deviation, just stdev, is, it's based on a sample. The difference is if you use the p one, it's dividing by n. The one with this one is dividing by n minus 1, which is appropriate for a sample. So let's highlight all those, Control Shift down arrow to get to the bottom of that list, press Enter, and you can see my very first one here was 1.70, whereas the theoretical value was 1.71, so pretty darn close. So once again, we can drag this all the way to the right. Hold down Shift, click on GS8, and then hold down Control and press Enter, and we got the standard deviation for every single one. So some are a little bit above, some are a little bit below, and we'll find the difference as well, equals that number minus the 1.71. And then we can click on the first one, we can scroll all the way to the right, hold down Shift, click Control, Enter. And there you go. So now we have the theoretical mean, the experimental mean, and the difference for every one of our 200 samples. We have the theoretical standard deviation, the experimental standard deviation based on our sample, and the difference for every single one of those. So let's go ahead and summarize some of this information. I have a little table over here. So we can calculate our average sample mean by averaging all of our experimental means. So the mean of all of those should be approximately 3.5. And actually, I'll show you kind of what we're doing at this point. I'm trying to verify kind of this statement of the essential limit theorem that states that the sample mean should follow a normal distribution. The mean should be equal to the true theoretical mean, whatever that is. In this case, it's 3.5. So if I find the mean of all my sample means, it should be pretty darn close to 3.5, or theoretically, it should be exactly. And then we'll also do the standard deviation here in a second. And then we will verify the normality by making a histogram. So right now we're kind of verifying this part, that the mean of our sample mean should be the same as the theoretical mean. So really what that means, I know I'm using a lot of the word mean a whole bunch here. So we have our sample means here, and we're going to find the mean of the sample means. So we're going to go equals average, and we have 200 different experimental means here, and we want to find the average of all of those. So I'm actually, maybe an easier way to do this would be to scroll all the way back to the beginning, click on the very first one, and then hold down Control, Shift, and then the right arrow, and that will have highlighted all of the experimental means. Press Enter, and it looks like my experimental mean was 3.4942, so pretty darn close to the 3.5, right? The average of my sample means was very, very close. Just about, basically verifying this, right? It's not going to be exactly the same, but theoretically it would be exactly the same. And we can do the same thing here. Actually, yeah, that's the next thing we're going to do here. So we're gonna find the theoretical standard deviation of x bar, which is equal to the standard deviation of x divided by the square root of our sample size. So first of all, we're going to find the average sample standard deviation. That's basically finding this value, or approximating this value. So the way that we can do that is we can use the average again, and we can do this now based on the experimental standard deviation. I'm gonna go back to the beginning here, click on the first one, Control Shift right arrow, and that's going to get me my average sample standard deviation. So it should have been about 1.71, but we actually got 1.7 here, so pretty darn close there as well. Now the theoretical standard error is this formula, right? So the standard error is basically saying how much should our sample mean differ from the population mean? Well, it turns out it should differ by about this number. So we can calculate that by taking the standard deviation and dividing by the square root of our sample size. So this standard deviation is the standard deviation of the individual dice rolls. So on the numerator there, I'm going to use the standard deviation .p again of the individual dice rolls, which is 1 through 6. And I'm going to divide that by the square root of the sample size. And our sample size was 100. So I'm going to divide that by the square root of 100. And I get about 0.1708. All right, so let's go ahead and calculate our sample standard error to see how close it is to the theoretical standard error. So the standard error is just saying, what was the standard deviation of our sample mean? So how far away was each sample mean from the true theoretical mean on average, right? And we can do that by taking the standard deviation, so standard deviation of the sample based on all of our sample means. So I'm going to highlight all of our sample means. Click on the first one, hold down Control Shift and the right arrow, and I've highlighted all of those. And then you can see I've got my sample error, sample standard error, which ended up being 0.1542, a little bit smaller than what it should have been, but nevertheless pretty close to the theoretical standard error there. Okay, the last thing to do is to verify one more part of the central limit theorem, which is the normality of the sample mean. So we have 200 sample means, which we generated, and those should follow a normal distribution. So if we plot our 200 sample means on a histogram, it should look like a normal distribution. So let's check that out. So let's scroll back to the beginning here, click on the first experimental mean, hold down Control Shift and the right arrow to highlight all the sample means, and then let's go to Insert. Let's insert a chart, and you might have to scroll back to the beginning to be able to see the chart here. And then we want to change this chart into a histogram here at the bottom. And then there you go. You can see that this does follow a pretty close to approximately normal distribution. Now let's change a couple of the kind of the titles to this distribution. So let's go here to customize, and let's change the chart and axis titles. So first, the main title here. Let's change this to results from 200. Results from 200 dice roll simulation with n equals 100. And let's center that, and then let's change this to our horizontal axis. We want that to be the sample mean. So these are the sample means on the horizontal axis. And then we need our vertical axis, and this is the frequency. Like how often did we get a sample mean between each of these kind of bins on the bottom? So we would put frequency here. And we can see the most frequent mean is towards the middle, and then it gets less and less likely to get a mean that's either much bigger or smaller than the average, which was 3.5, and that's what we call a normal distribution. So we have verified that statement. So let's go ahead and let's move this chart to its own sheet, and let's change that sheet to sample mean histogram. All right, so there you go. That is the end of this first part of this Excel lab here. So we have kind of verified the central limit theorem using the simulation of dice. So now let's go ahead to the normal distribution tab here, and this is where we are going to basically create a model that will calculate probabilities related to the normal distribution for us. So there are three different main problems that are done related to the normal distribution and probabilities, and we're gonna create a model that will do all three of those for us. So let me just kind of give you a preview of kind of what we're trying to do here. Based on my PowerPoint here. So one thing we're going to want to do is we're going to want to be able to take information from a normal distribution and calculate probabilities. So here's an example that I use. It's related to Godzilla. He likes to destroy cities, and the amount of damage he inflicts follows a normal distribution with a mean of $100 million of damage and a standard deviation of $10 million. So that means we have a normal distribution set up at 100 in the middle with a standard deviation of 10. And maybe what we want to do is we want to find probabilities related to that, right? So maybe we want to find the probability where greater than 115 or maybe less than 115. That's going to be what this first model is going to do. So I'm gonna show you how to do that one, and then I'll show you what these other ones are. But first, we're trying to do this. We're trying to, on a normal distribution, can we find the probability where either greater than, here's a greater than, less than, or between. Here's a between, or between two different numbers. I guess I don't have a less than in here, but we have a greater than, we have a less than, we have a between, and then we're also going to do a less than. So you can see those three options. We're going to get all three of them at the same time, right? The chance that we're less than some value, the chance that we're greater than that same value, and the chance that we're between two separate values. So before we do that, we're going to want to set this up so that's kind of more of a user-friendly model. And what I mean by that is we want to have certain cells colored in different colors so that they're very clear that they are either input or output cells. So what I'm going to do is the ones up here on top are going to represent input cells. So I'm going to highlight these cells. I'm going to hold down Control, and I'm going to highlight the other ones as well. If that doesn't work, you can just do them one at a time, but it's a little faster to do them all at once. So if you hold down Control, you can select those non-adjacent ranges. Let's go to our fill color, and let's change this to the light green 3. And let's do the same thing here with these ones down here, and let's highlight these 3 by holding down Control, and let's change this to the red 3, the light red 3. And then we're also going to want a little key here that indicates to the user what the input and the output cells are. So I'm gonna change this cell right here also to maybe the light red, and maybe this cell as a light green. And I'm going to label these. So I'm going to tell my user, oh, these are the input cells. Any of the green ones are input, and any of the red ones are outputs. So the user should be changing the green cells, and the red cells are going to get changed based on how the green cells are, what's inputted in the green cells. So just to make sure we can kind of verify our formulas once we've typed some in, let's just type in a couple of values into the green cells as some inputs. So let's just say we have a normal distribution. The mean is 100, the standard deviation is 10, and we have a couple different values. So this is matching the same example here, a mean of 100 and a standard deviation of 10 million. But I'm just using 10 rather than the millions, right? And let's say we want to find some probabilities related to that. So the first thing we're going to do is we're going to calculate a couple of z-scores. So we're gonna say, okay, we got an x value of 90 or an x value of 105. Let's find the z-scores related to those, which is kind of they'd also be corresponding values on the distribution. So you can kind of see I've put those here on the picture. We're going to find those values. And the z-score formula is right here. It's you can take the observed value, like the amount of destruction that Godzilla did, I guess would be in our example. The value on the distribution. It's going to be our x1 minus the mean and divide by the standard deviation, and that will give us our z-score. The z-score is going to tell us how far away our observation is from the mean in terms of standard deviations. So let's do that here. We're going to do equals. Open parentheses, we're going to do this for z1, we're going to do x1 minus the mean, which is 100, and divide that by the standard deviation, which is the 10. And that is giving me, why is that giving me -1 there? Take the first value, x, minus the mean, which is 100, and divide, oh yeah, that is right, -1 does sound right there. Yeah, it should be -1 because 90 is 10 below 100, so yeah, that's telling us we're 1 standard deviation below the mean, so that does seem right. Let's do the same thing for the z2 here. So let's do this based on z2. So this is going to be equal to x2 minus the mean and dividing by the standard deviation. And that one apparently gives us 0.5. So now we have those z-scores that tell us, the x1 is 1 standard deviation below the mean, the x2 is half a standard deviation above the mean. Let's find the chance that we are either less than, greater than, or between those two numbers. So first let's do the less than probability, and I realize I don't have a picture for this, but this would be kind of like if we had a number right here like the 115, the chance that we are less than that 115. And the way that we can do that is in our case, it would be less than the 90. The way we can do that is we can use a function called norm.dist. So type in equals norm.dist. We're going to do this for less than x1. So we're going to click on the x1 for our x. And then we need the mean and the standard deviation. So the mean is 100, and the standard deviation is the 10. And then finally, we need the cumulative argument. You're always going to put that as true. And there we go. We get the probability we are less than 90 is apparently about 16%. And now the probability that we are greater than the same number is going to be, well, it's just the complement of this number, right? So it's kind of like here, if I had the chance I was less than 115, then I could find the chance that I was greater than 115 by just taking 1 and subtracting the other one, because those two would be complements, right? So kind of a shortcut here to find the greater than would be I can just take 1 minus the other one, and that is going to give me the probability I'm greater than that same value. Now the between is a little bit trickier. So the between here, says, okay, I want to be between two different numbers. And the way we're going to have to do this is kind of a little bit tricky here, but what we're going to end up doing is if we put in the norm.dist function for 110, what it's going to tell us is the chance that we are less than 110. So everything less than 110. So if I did the norm.dist with 110, it's going to give me this green area, but it's also going to give me like this white area here. But that's not what we want. We just want the green area in between, right? So what we end up having to do is put the norm.dist for our second x value, and then we have to end up subtracting the value for 88, because the value for 88 would represent the number in this tail, right? This function always gives us the area to the left. So if I do the area to the left of 110, I get everything to the left of 110, and I subtract off what's left of 88, I will be left with this area in the middle. So let's go ahead and do that. So I'm going to use the norm.dist function again. I'm going to do it for x2, comma, the same mean, the same standard deviation, and still true. And this number here, they're giving me the number, it's 0.69. That would be the chance that I'm less than my x2. So that would be the green and the white area together. But I don't want the white area, so I'm going to subtract off the white area. The white area is what's less than 88, or in this case, less than our x1, which is 90, right? So I'm going to subtract off what's less than 90, which we actually already found that number. That was this number right here, the chance we're less than x1. So I can subtract off that number, and that's going to give me the probability, which ends up being about 53%. So now you can experiment with, you can change these numbers, and these numbers will all change down here. It will calculate the probability that you're, between two values, greater than or less than a value based on your inputs that are above. But I'm going to revert this back to how we had it. Next, we're going to do a problem type number 3 is what I've called it here, which is kind of similar to this first one. The difference here is now we're trying to find a probability related to x bar. So whereas in this first case, we were trying to find the chance that, a single observation was either greater than, less than, or between two numbers. Now we're going to say, oh, what's the chance we find a sample mean? And that sample mean is either less than some number, greater than, or between two different numbers. So let me see if I can find an example of that here in my PowerPoint. I think this would be the example here. So I had an example with commute distance. So like people were commuting to work, and I guess the average was 15 distance? 15 miles with a standard deviation of 4. Well, we're trying to ask a question about the mean, right? So what's the chance that the mean from 25 different people who commute is less than 12 miles? So if we're talking about the mean, we're actually talking about the distribution of x bar. This kind of relates again to that central limit theorem. And the mean of that distribution would still be whatever that mean was, but we have to kind of find this new standard deviation, which is what we call the standard error. We were dealing with that before. We can find this value, this 0.8 value, by taking the value that was given divided by the square root of our sample size. So you'll see that I have that in here as well. I got an option for the standard error. We're going to have to calculate that. That's going to be this number over here. So just like before, we're going to be finding some area on the distribution. Here I have like a less than, but we could also be either greater than or between two numbers, right? So let's enter in some numbers just like we did before. The ones I have for this are going to be 100, 10, 36, 97, and 102. So you could put in other numbers there, but if you want to kind of match my numbers, those are the numbers that you would need. So first of all, let's go ahead and calculate our standard error. That's the standard deviation of x bar. You can always find that by taking the standard deviation of your distribution and dividing by your sample size, or dividing by the square root of your sample size. So that's what I'm going to do right here. I'm going to take the standard deviation of the distribution that was given and divide that by the square root, so SQRT for square root, of the sample size, which is our n value, which we put in as 36 here. Close parentheses, and we're going to find that the standard error is 1.67. Really what that's saying is if I was to get a sample mean from this distribution and my sample size was 36, I could expect it to be about 1.5, a little bit over 1.5 away from 100, the actual mean on average. So a sample mean would be about 1.6 away from 100 on average. And then we have z-scores we're going to calculate. So the z-scores are slightly different. So the z-score is going to be calculated using this formula here. So we're going to take x bar minus mu and divide by that value we just found, the standard error. So that's what I'm going to do right here, where the x bar is here, the mu is here, and then the standard error is this value right here. So let's do that. So that's going to be x bar. So we're going to do the x bar 1 here. Minus mu is 100 divided by the standard error here. We get negative 1.8, and we got to do it as well for x bar 2. So x bar 2 minus the mean the population mean, and divide by the standard error, which ends up being 1.2. There you go. So, and then we can go ahead and do the probabilities the same way we did them last time. So let's go ahead and do that. So this is going to be norm.dist. The x now is going to be the x bar. The mean is the population mean. And the standard error, or sorry, the standard deviation is going to be the standard error that we just found. And we're going to put true for cumulative. Oops, let's get out of that. And then we'll do 1 minus that for the greater than. So basically what we just found here, the less than is finding like this area to the left. So maybe we have some sample mean. The chance we are less than that is this number here, 0.0359. The chance we're greater than that would be 1 minus that. That's the chance we're greater. It's going to be the complement. And the chance we're between, just like before, we can take the chance that we are less than the x2, and then we can subtract the less than area. So once again, I don't know if I have a picture of this one. I don't really have a picture of this one, but it kind of mirrors the one that we did before, right? So if you find the probability you're less than the upper one, that's actually the white area and the green area, but you're going to have to subtract off this white area to get the area in between. So we're going to do equals norm.dist. Our x is going to be our x2 this time with the 100 mean and the standard deviation of 10. Actually, not 10, sorry. We should be using the standard error there. And then true for cumulative. And then we need to subtract off the chance that we are less than x bar 1 to find the area in the middle, which ends up being about 0.849 in this case. Now, something I forgot to mention on the other one, if you're going to experiment with changing these numbers, make sure your x2 is bigger than your x1. We are assuming that x2 is the one on the right and the x1 is the one on the left, because if you enter in a number that's like smaller here, so if I put in like 90 here, you're going to end up getting some negative probabilities, which don't make a lot of sense. So make sure this second number here, as well as the second number here, are larger than the numbers above them, the x bars right above them. All right, finally we can do a problem type number 2. So this is like you're trying to find a value on your distribution. So let me give you an example of that. Let's see here. Where do we have an example of that? Right here. Actually, right here. So this is like saying, okay, Godzilla, he inflicts $100 million of damage on average with a standard deviation of 10 million. What would, how much damage would he have to inflict to be at like the 90th percentile? Or, here it says at 90% of the cities, at most he's inflicting how much damage? So that's saying, oh, what's the value such that 90% would be to the left? So this is kind of backwards. We already have that probability or area, and we're trying to find the value on the distribution. And so first of all, we're going to have to specify that area. So that's what we have here, probability to the left. And I'm going to enter in 0.3 for that with 10 and 100. So if they had 0.9 here, you could do it with 0.9, but I'm just going to do it with 0.3 because that's what I had in my notes. And therefore, if you have some probability to the left, you have the kind of the complement probability to the right. So I can do 1 minus that 0.3, and that's going to give me the probability to the right. So if it's 90% to the left, it would be 10% to the right. If it's 30% to the left, it'd be 70% to the right. I can find the z-score corresponding to that by using, we usually use inverse norm with a TI-84, but here we can use a function called norm.in, kind of like backwards there. And the x that is asking for is actually the probability to the left. So we're going to put in the probability to the left, the mean, and the standard deviation. And that's going to tell me the z-score. Actually, no, sorry. If I'm going to do a z-score here, I need 0 and 1, right? Sorry about that. I'm going to need 0 and 1. Because the mean of a z distribution is 0, it's centered at 0, and the standard deviation is 1. So that's going to give me the z-score of negative 0.52. And I can find the raw score by using the raw score formula. So the raw score formula says, okay, if you got a z-score, you can take that and multiply it by the standard deviation and add the mean, and therefore you will get the raw score. So if I take that z-score, I multiply by the standard deviation, and I add the mean, that's going to give me the raw score. So basically this is saying, if we took our Godzilla example, if we want to be at the 30th percentile, so the amount of damage such that 30% of the time it's less, well, apparently that number would be 94.7. So if Godzilla went to a city and he inflicted 94.7576% or $94.76 million of damage, then that 30% of the time he would be less than that number. Okay, a little bit harder to kind of explain that one, but hopefully you can kind of see that based on the picture here. This one was 90%, And you can see here they got that 112. So if I put in 90%, I should also get the same answer as them, right? And you can see there I do get that 112.81. They rounded to 1 decimal there, it looks like. All right, so we can just clean this up a little bit. So let's round anything that's not a probability to 2 decimals. So I'm gonna select these by holding down Control and selecting all the ones that aren't probabilities. And I'm gonna shift the decimals here, so I'll get 2 decimals. And then I'm gonna do the same thing for the probabilities, but I'm gonna do those to 4 decimals. So let's do that. And there you go. So now we have kind of our completed model. Now we can, if we want to, kind of we could kind of test this with a couple of questions. So maybe I'll do that here really quick. So let's grab this and let's make this a little bit smaller here. So maybe I can see like this. And I have just like 3 examples just to make sure that this is working correctly. So it says, okay, first one, for a normal distribution, if your mean was 55, I'm going to start typing these numbers in. Mean of 55, a standard deviation of 12. What's the probability of value is between 30 and 60? So that's asking the chance we're between 30 and 60, and you can see here, oh, it should be 64.29, and indeed we do get 64.29. It looks like I actually went 5 decimals here. Let me change that. And one more that I wanted. There we go. Now we have 4. So you can see here I do get that 64.29. And the next one's going to be based on the second one here. So for a distribution with a mean of 750 and a standard deviation of 96, what's the chance we get a sample mean with a sample size of 87? That's somewhere between 730 and 815. And you can see here I do get the 97.4. I'm also getting the same answer for this. Why is that ended up being the same? It should not be the same there. This one should be based on... Okay, I thought there was an error for a second, but there really is no error. This is just kind of... I actually kind of had an example that gave us a little bit out there value. We have a z-score of 6.32. So actually, that's pretty darn far out there. So that actually made it so that the greater than probability was the same as the between probability. I may end up changing this one if you're working with the same document. But in this case, this is correct. 0.974 is what we got with this information. And the last one, what's the 80th percentile? So 80th percentile means my probability to the left is going to be 0.8. Maybe I want to make this a little bigger so I can see that as well. And then they say, let's see here, 80th percentile for the distribution which has a mean of 93 and a standard deviation of 27, and that number should be 115.72, and you can see here it does indeed come to 115.72. So just kind of verifying that the model is appearing to work. All right, I think that's all I have for this video, so hopefully you found this helpful. I got a couple other examples here related to coin flips and an exponential distribution, so I encourage you to go ahead and try those out.